let's have the talk. So Eva, please go ahead.
Thank you. Thanks a lot. Thanks a lot to the organizers for giving me this opportunity to speak at this conference. And I really wish I could attend in person. Yes, I would be speaking about a cohomological version of the singular Hodge conjecture. Are my slides, etc., everything visible?
Yeah, that's visible. Yeah, please go.
Okay, great. Okay, so let's get started. So the thing is that this is quite a technical talk, as in the material itself is very technical. I haven't tried to make it overly technical, but I kind of know that it is technical, and I also know that I am not there in person, so I cannot really judge from people's faces whether they are understanding or not, or they're completely lost. And normally I look at my audience a lot to see how things are going. If people start opening their laptops, I know it's gone. So I cannot tell from here, but what you can do is that whenever you have questions, you can stop me. For my part, I try to put as much in the beginning in words, rather than mathematical symbols as possible, so that we get an idea of what's going on. And I also try to recall definitions that I think more or less, in the beginning at least, that most people actually already know. So, but if you don't, you can always stop me, okay? So with that, so we are always going to be over C, and a pure Hodge structure of weight R, which I will denote by this VZVPQ, consists of a finitely generated free abelian group, a lattice, VZ, and a decomposition of the complexification of the lattice, such that I can write VC as the complexification as VPQ, where P plus Q equals R, for as I vary the P in Q. And they have to satisfy the property that VPQ is actually equal to VPQ conjugate. Okay, so this is the Hodge symmetry. Equivalently, I can define a pure Hodge structure on VC by giving a filtration. Okay, so this is increasing filtration, and such that VC can be written as this. Okay, so I can basically, so I have these two definitions, and I can go from one to the other. So this is how I define a pure Hodge structure. I think most people already know this. And now for the talk, I will first give things in. So the talk, as you know, the title says that I want to discuss a cohomological version of the singular Hodge conjecture. So maybe for beginners, it's important to understand what is the classical Hodge conjecture. Forget about the singular Hodge conjecture. So first, I'm just going to give the definitions related to the classical Hodge conjecture. So okay, so X smooth projective variety of, say, dimension n. Then by Hodge's theorem, we know that actually H2P X with the singular cohomology in Q admits this Hodge decomposition. Okay. Now for R equal to 2P, the elements of HPP, so we have the Hodge decomposition, and if we let R equal to 2P, the elements of HPP, which is H2P intersect HPP XC, so we have the XZ intersect, so all the Hodge decomposition is always for C, so we intersect with C, are called Hodge classes. Okay, so this is just a definition, a very simple definition. You have these elements and you call them Hodge classes. Okay, now an algebraic cycle of codimension P is a formal linear combination of irreducible codimension P subvarieties of X, right? So X, you just take a smooth projective variety and you have an algebraic cycle of codimension P. You just define this as a formal linear combination of irreducible codimension P subvarieties. Okay, then we have the free abelian group generated by these codimension P algebraic cycles, and this is denoted ZP. And we have the cycle class map, which basically takes a algebraic cycle, so ZP X tensor Q. So here the coefficients with Q, and it spits out a class. Okay, so this is the cycle class map, and it is not hard to show that actually the image of the cycle class map lies in the Hodge classes. So I just defined Hodge classes as this intersection for the H2PXQ with HPPXC. Okay. And now what I'm saying is that when I look at this map, the image lies in here. Okay, so this is not hard to show. But what the classical Hodge conjecture claims, so I will keep calling it sometimes classical to make sure that we understand that I'm then talking in the for the smooth variety. So the classical Hodge conjecture says that, okay, you know that the algebraic cycles, the image of the algebraic cycles under this cycle class map is in the Hodge classes. Okay, but what about the Hodge classes? Does every rational PP Hodge class always come from an algebraic cycle? So more precisely, is the cycle class map surjective? So you know that the image of this thing was going to be in here, but more important, is it surjective? So does every Hodge class really come from an algebraic cycle? Okay. And why did Hodge think that this was a good idea or this was plausible? Is that it is certainly true for P equal 1, right? So you have Lefschetz 1, which tells you that every 1 class really comes from a divisor. Okay, so, and then he went into a big leap of faith and said that this is going to be true for all P. Okay, and that is the Hodge conjecture, that this is true for every P. Okay, so the evidence supporting the Hodge conjecture is actually very minimal. The Hodge conjecture has been now open for like 70 years, and there isn't too much evidence. So the evidence that we have is that it is certainly true for P equal 1, Lefschetz 1 for any variety. For P equal 1, it's true. But is it true for all P's for some varieties? Yes, it is true for very general abelian varieties. Okay, so what do I mean by very general? In general, so the thing is that I do use these terms quite a bit. So I think it is a good idea to recall the definition. I think most people already know this. So in general, so an element is general if it lies in the complement of finitely many proper closed subsets, okay? And it is very general if it is in the complement of countably many proper closed subsets. So whenever I say a very general abelian variety, I mean that I take the set of all abelian varieties, and if I was to remove countably many proper closed subsets, the things that are remaining would be very general, okay? And the same would apply to curves or whatever else I take, and I will soon be taking those. Okay, so the Hodge conjecture is not true. It is not known to be true for an arbitrary abelian variety, but it is true for a very general abelian variety. Okay. Okay. Now, the thing is that if I understand correctly, this crowd is very interested in moduli spaces, and most importantly in moduli spaces of sheaves over curves. So we have some nice examples for the Hodge conjecture, actually thanks to some members in the audience, for moduli spaces of sheaves on curves. Let me recall those. So suppose I take X to be a very general smooth projective curve, RD to be coprime integers, and L aligned bundle on X of degree D. So its rank is, its degree is coprime to the rank. We have that, firstly, if I just look at the moduli space of degree 0 line bundles, the Jacobian of X, then this satisfies the Hodge conjecture. So this is a rather old result, and to be honest, I'm not exactly sure who this is due to, but it is in the book of Birkenhagen and Lange. And this is true again if X is a very general smooth projective curve. Okay, so it is not true in general. Again, you need it to be a very general smooth projective curve. Then the Jacobian of X is does satisfy the Hodge conjecture. Okay. the moduli space now. So the Jacobian of X. So Jacobian is the moduli space of degree 0 line bundles. If I go up a bit more, that is to say that if I take the moduli space of stable rank R determinant L vector bundles on X, again, X a very general smooth projective curve, then this satisfies the Hodge conjecture. Okay, so in the case of rank 2, this was shown by Balaji, King, and Newstead. And in the case of rank R, this was shown by Biswas and Narasimhan. Okay, so as long as we have this assumption, and the thing is that all of these results really need the assumption again that X is very general smooth projective curve, because they actually use that this is true for the Jacobian of X, and for that you have this condition that it's only true if the curve is very general. So this is a kind of a error carried forward. You have to keep this condition. But okay, so the simplest moduli spaces of sheaves that we can think of on a curve, we already we already know that the Hodge conjecture is satisfied. Okay.
You need R and D to be co-prime in that example.
Hang on, I can't hear you. Sorry.
Yeah, rank and degree has to be co-prime.
Yes. Rank and degree need to be co-prime. Yes, because if rank and degree are not co-prime, I mean, so RD are co-prime and L is a line bundle on X of degree D. So yeah, you can do it for arbitrary rank, but rank and degree need to be co-prime, because I think even even for a very general, I mean, for a smooth projective curve, if you just look at the moduli space of rank R degree D bundles, you know that if the rank and degree are not co-prime, then it need not be smooth. And that's interesting, because this is where, I mean, there is something here related to this this talk. So yeah, most of the time, the Hodge conjecture, the classical Hodge conjecture, always needs your variety to be smooth. Okay, so this is, I mean, it is defined that way. So you need the variety to be smooth, and the moduli space is not going to be smooth if rank and degree are not co-prime. Okay, thank you for the question. So so the question that we are interested in, which I'm happy that we already started here, is that, okay, now, so the formulation for the Hodge conjecture is for a smooth projective variety. Can we say something if X is singular? Do we have a similar formulation of the Hodge conjecture? And here the thing is that it is, so this is a question. This is the question of my talk, and maybe before I really launch into the answer, because I'm sure that, I mean, the audience is full of people who have been working on this for years or know this stuff. So I'm sure that somebody's going to point out that, but isn't there a homological version by Janssen? And yes, there is a homological version by Janssen, but it is still unproven. And moreover, it's the homological version. So I should make a distinction, and I did in the title of my talk, that I'm interested in the cohomological version. So the classical Hodge conjecture is to do with cohomology, is in the cohomological setting. And again, the version I'm interested in is again going to be in the cohomological setting. So yes, there is a homological version already by Janssen, which is also not proven, so we don't have any results. But yes, if you're interested, it is probably something you can look into. Okay, so my problem is that I really want to look at the Hodge conjecture, the cohomological version. And the very first thing is that, okay, when I started giving this talk, I very quickly, and I guess not very calmly in the beginning, I gave you the group of algebraic cycles and the cycle class map, and I said this is how I define the algebraic cycles. This is how I define the Hodge classes. So obviously the question is that, do I have all these ingredients for the singular variety? So this is the first question, right? So if I want to write down the cohomological version, I need to have the ingredients. So the ingredients is actually not there, or it is there, but not straightforward. So if you look at the classical Chow group, then this is not compatible with arbitrary pullback morphisms. Okay, So the Chow group is just basically, I'm looking at the group of algebraic cycles, and I'm modding out by rational equivalence. Okay, so I think everybody here probably knows this well, so I will just keep going, but if you don't, we can, I mean, okay, so rational equivalence, two varieties are said to be rational equivalents. If you can kind of take, say, X, so you want to look at two varieties that are rational equivalent in X, okay, we would say that if there exists an irreducible subvariety, say W or W, which does not lie, which is not contained in any fiber of X cross P1, and I can say that if two varieties, let's say y0 and y infinity in X are going to be rationally equivalent, if the intersection of W with X cross P1 is the intersection of W with X cross the fiber over 0 is X0, and if it is the fiber over infinity is X infinity. So I have basically rational equivalence means I can interpolate from one to the other. So I think everybody already knows this definition, and I did not write it down, but I know from myself that sometimes when I'm sitting in talks, I wonder, okay, there were many equivalences, right? So which equivalence is this? So this is that one, the one where you can go over P1 and you get interpolate from one to the other. Okay, so the classical Chow group is basically looking at the group of algebraic cycles modulo this equivalence. Okay, so the thing is that if you make the variety singular, then this group is not compatible with arbitrary pullback morphisms. And that's a very key property that you need in order to define these things. So you basically cannot use what you have been doing already for the smooth setting. Okay, so you use the operational Chow group by Fulton and McPherson, and this is actually very complicated, and I was really wondering about how much of this definition should I give, because if you haven't seen this or the operational Chow group, me writing down the entire definition, everything, I do not know how much it's how enlightening it's going to be. But basically what you have to understand is that if my variety is not smooth, in fact, if it's not even projective, it's quasi-projective, I have something like a Chow group, the operational Chow group by Fulton and McPherson, that has some very, very nice properties. So you can just take this as a black box. Just bear in mind that this is not exactly the same as the other one, but I mean, in terms of definition, but you don't have to care. So you can replace the Chow group thing with the operational Chow group. What about the cycle class map? Do I still have a cycle class map? And one of the many issues is that why you cannot just take your definitions that you had for the smooth variety and put it for the singular, is that actually when you have a singular variety, the Hodge structure is no longer pure. So what I told you that we have the pure Hodge structure. I mean, I haven't gone too far, so I can keep now going back, but later on I'll just have to rely on your memory. So I said that I have this, right? A pure Hodge structure. So when my variety is smooth projective, then by Hodge's theorem, I know that I have the Hodge decomposition, and I have a pure Hodge structure. I always have a pure Hodge structure. But when the variety is singular, no, I have a problem. I have a Hodge structure, but it is no longer pure. So if it is no longer pure, then this nice, definition of, okay, I just take a lattice, I take its complexification, I take its decomposition and whatnot, actually gets a little bit more complicated. So what is a mixed Hodge structure? So whenever I have a singular variety, I don't have a pure Hodge structure, I have a mixed Hodge structure. So mixed Hodge structure is a little bit more complicated. So here I mean V. I mean, what I had V back then, I sometimes write V, sometimes write H. So I again have my lattice that I had before. And now I have, instead of just the Hodge filtration, the F upper dot, I also have the weight filtration, okay? And here, so the weight filtration is first, this is an increasing weight filtration. And this is defined on on the HQ. So that is the lattice tensored with Q. And I have a decreasing filtration, again, for the complexification of the lattice, such that F dot defines a pure Hodge structure on the graded pieces. Okay, so this GRWK. So that is that I take the graded pieces of this weight filtration. I take the pieces of this weight filtration. I quotient WK plus 1 by WK, and on that I have a Hodge structure of weight K. Okay, so the filtration is giving me a pure Hodge structure on the graded pieces. Okay, so obviously this is a little bit more complicated here. I have the weight filtration, and my Hodge filtration is on the graded pieces. Okay, so so this is what I always have. I always have for a singular variety. Now, if I have the, as I said, I didn't want to write too much about the operational Chow group, but I will just quickly say some things. So the operational Chow group, and you can just take this as a black box, the definition. I mean, it comes from this very cochains and hyperenvelopes and whatnot. And I don't think we're going to learn too much if I sit down and give the definition in detail. But you have to know that the operational Chow group has several nice properties. Okay, first, it exists for singular as well as quasi-projective varieties. Secondly, if X is not singular, then like most good definitions, you know, when you're extending a definition from something smooth to singular, you want that if the variety was smooth, you'd get the same thing, and it does. So if X is non-singular, it is the classical Chow group, i.e. This is just ZP modular rational equivalence. Okay. Now, if X is not singular and you take a compactification of X with this boundary, so you are saying that X is non-singular, but I mean, it need not be projective. Yeah. So you take a compactification. So because this Chow group exists for singular as well as quasi-projective varieties. So this is a very important thing, that it actually exists for quasi-projective varieties. So then we say that we take X bar compactification, and this the boundary. Then we have a very nice exact sequence. Okay, and where APC is just the compactly supported operational Chow cohomology. Okay. Now, if X is the union of two proper closed subvarieties, X1 and X2, then another nice thing is that we can really put the operational Chow groups for the X and X1 and X2 in this very nice sequence. Okay. So these are very nice properties, and hopefully if I reach the end, well, we will see why these properties are very useful. Okay, maybe I should hurry up a bit. So how long do I have? 1 hour, right? Okay. Okay, so I have the cycle class map from Bloch-Gille-Soulé. So okay, so for the part of the Chow group, we figured out that okay, we don't use the normal Chow group, but we can use the operational Chow group. Good enough. Okay, but what about the cycle class map? So we also need something for the cycle class map. And this is that if you take a singular variety and you have your operational Chow group, the first thing you would think is that, okay, now I just do exactly what I had before, which is that I just take APX tensor Q and I send it to H2PXQ, and I know that I have these, I have the decomposition and whatnot, but although a little bit different. So this should work. And there's a result by Bertotaro that says that actually you can have such a map, but it will not have any good properties. So you don't have your, you don't just take your old cycle class map, put in the operational Chow group and get a cycle class map. No, that doesn't work. But what we do have by Bloch-Gille-Soulé is that there is a functorial cycle class map, not to the whole H2P(x)3, but to the 2P graded piece. Okay. So if you have the 2P graded piece, you do have a nice cycle class map. And this, when I say it has good properties, I mean that it needs to be functorial, etc. And yes, this one it is. Okay, so this is a little bit of an alteration, but we have it. And again, like a good definition, the point is that if X is non-singular, then this agrees with the usual cycle class map. So we are in good shape. Okay. So okay. So now the thing is that we have a Chow group, operational Chow group. We have a functorial cycle class map. So obviously we can now try to figure out what we mean by algebraic cohomology group, algebraic cycles, and what do we mean by the Hodge cycles. So we define the following. For X projective, we can define the algebraic cohomology group to be the image of the cycle class map. Okay, so simple. We just, how do we define our algebraic group? We just algebraic cycle group, we just define it as basically the image. Okay, good. But then what is our cohomological formulation for the Hodge conjecture? So our cohomological formulation for the Hodge conjecture is as follows. If you take X to be a projective variety of dimension n, and you suppose that the singular locus of X, X sing, is of dimension at most p minus 1, then we say that X satisfies the singular Hodge conjecture in weight p if the image of the cycle class map is actually equal to the Hodge classes. And here you're really defining the Hodge classes in very analogous way to what you had for the smooth setting. Okay, so you say that the singular Hodge conjecture holds in weight p if this happens. Okay, so obviously the singular Hodge conjecture says that this statement is true for all p. Okay, so again, like any good definition, we want that the singular Hodge conjecture should just be the classical Hodge conjecture if the thing is smooth, and it is. So the formulation is such that if X was smooth, this would really just be the classical Hodge conjecture. Okay, now the goal of this work is to basically give a criterion for a singular variety to satisfy the singular Hodge conjecture, because it's very nice coming up with what possible statement it should be, but it's not much point if there are not many things satisfying the conjecture, right? We just have another conjecture. Okay, so the main goal of this work with Ananyo is to really give a criterion for when a singular variety would satisfy the singular Hodge conjecture. And the strategy, so the thing is that I understand that this stuff is a little bit technical, and I also understand that I'm not there, so it's not very easy to gauge if I'm going too fast or too slow. So as I said, I wrote things down in words first. So here I'm going to give you a strategy, which maybe to experts, all these things seem very vague, but I will make it precise very soon, and I will go through things very, very precisely. But first, I just wanted to motivate everything, just by words and see how much I can avoid terminology. And as you see, even then, there is quite a bit of terminology. So the strategy to basically giving a criterion for a variety to satisfy this singular Hodge conjecture is kind of the things that you would guess, right? The first thing that you would guess is that, okay, I might know how things work, let's say, for a smooth variety. Then I want to know how it works for a singular variety. Okay, so one possible strategy, which is the the stupidest thing you can think of, and almost always what you try to do first, is to see if you can embed this singular variety in a flat family of projective varieties, such that your given variety is a singular fiber and all the rest of them are smooth. So if all the rest of them are smooth, then they probably already have whatever property you're looking for, and then you need to figure out a way of, how you could get that property for the singular thing using the smooth fibers. Okay, so this is the textbook thing, bookkeeping almost. So you do this. So yes, this is the first thing we do. So we embed the singular variety in a flat family of projective varieties such that the given variety is the singular fiber. Okay, then we equip the singular fiber with the limit mixed Hodge structure due to Schmidt. So you don't know what's going on in here. What basically all this Hodge conjecture, right, is taking place in the cohomology of the variety, right? Now you want to understand some things about the cohomology of the singular fiber from the cohomology of the smooth fibers, because let's say the smooth fibers already satisfy some good properties. Say they satisfy the Hodge conjecture. So what would you do? You would find a way of connecting the cohomology of the singular fiber to the cohomology of the smooth fiber. And there's a very nice theory already which exists, which does this. And it doesn't just connect the cohomology, it also basically connects the Hodge structures. So it looks at how the Hodge structures vary. So if we equip the singular fiber with the limit mixed Hodge structure, and I will give very briefly, I will define what is the limit mixed Hodge structure. Then there is actually a morphism of mixed Hodge structures from the cohomology of the singular fiber to that of the smooth. Okay. And if I do not take the limit mixed Hodge structure, then I do not actually get this morphism, which is the specialization morphism. This doesn't really come as a morphism of mixed Hodge structures. So this is a subtle point. Okay, so supposing I have this, so then I basically say, okay, if a very general fiber in the family satisfies the Hodge conjecture, does the central fiber satisfy the Hodge and the singular Hodge conjecture? Okay, so if a very general fiber, which was smooth, satisfies the Hodge conjecture, does the central fiber, which was singular, satisfy the singular Hodge conjecture? So now my question becomes this, okay? And this sounds like the kind of thing that more or less anybody would come up with. But there are some subtleties. There are some things that can go wrong. So I will go into that. But the first thing is that what is a limit mixed Hodge structure? And as I said, I'm not going to spend too much time on this, because if you have never seen this before, I do not know how much you're going to learn just from me saying this right now. But if you have, then it's a nice recall. So basically, I take a flat family of projective varieties, say smooth over the punctured disk, okay? But the fiber over zero is singular. And I have the universal covering of the punctured disk. And then I denote by chi infinity the pullback of this family to the upper half plane, H. And I know by Erzman's theorem that given any S, there is a canonical identification between the cohomology of the pullback of the family to the upper half plane, this, and the cohomology of any fiber. Okay, so this is so here I'm working over the punctured disk. Okay, so the things are smooth. So first, I know that this is happening for all the smooth fibers. I know that the cohomology is going to be the same. Okay, then the Hodge filtration induces so I need 2-3 things, right? So for a mixed Hodge structure, I needed the Hodge filtration and I needed the weight filtration. And so I get the Hodge filtration very simply. I mean, I just have my this thing and I pull back and I can extend it, and okay, I get what I need. And then for the weight filtration, I need to do a little bit more work. Okay, so the Hodge filtration on this induces a Hodge filtration on chi infinity. So this is the I mean, I will sometimes call this just the limit Okay, so it induces, because there is a canonical identification, I can use the Hodge filtration on this to basically get a Hodge filtration on the continuity. Okay, and I call this AFS. And the limit is basically the limit of this thing twisted by the monodromy action as the imaginary part of S tends to infinity. So if you know these things, you know exactly what I'm talking about. And if you don't, then it's kind of hard to explain. But vaguely speaking, this is what's going on. Okay, so I have that the limit Hodge filtration is just basically the limit of this Hodge filtration on this twisted by the monodromy action, and then I just see what happens as the imaginary part of S tends to infinity. Okay. Now the specialization morphism basically relates the mixed Hodge structure on the cohomology of the singular fiber to that of a general fiber, equipped with the limit mixed Hodge structure. Okay, so as I mentioned before, that now if you use this limit mixed Hodge structure, you actually get a morphism of mixed Hodge structures between these two cohomology groups. Okay, and the good, I mean, this is, so you have a morphism, this is very good, but then in general, this is neither surjective nor injective. So you just know that there is a morphism. Okay, and our goal in this work is to show that for the algebraic classes, so when instead of just looking at all of these things, if we just look at the algebraic classes, then it is surjective and we study the kernel, basically. So I will also make a remark about this strategy a bit later on. But so up until this point, you think that, okay, more or less we could have guessed this, right? We could have guessed that this is what we would do. So what is new? What is interesting? And the problem is that this is actually not enough. So you have your specialization morphism, you have all the information for the smooth fiber, you can connect the cohomology of the singular fiber to that of the smooth fiber, you have this morphism of mixed Hodge structures, you can get a lot of things, yes. But there are problems. Why? Because one very basic problem is that the rank of the Hodge lattice of the limit mixed Hodge structure can be larger than that of the Hodge lattice of the general fiber. Okay, so you have an identification, yes, but the problem is that the Hodge lattice, the underlying lattice, might not have the same rank. And so when you're looking at the integral points, there can be problems. So why is this a problem? Well, the problem is that the issue is that we really want to be able to tell, not just get a morphism between the different cohomology groups. We want more, right? We want to be able to tell all the Hodge classes of the singular fiber from those of the smooth fiber.
So in the one question, please. Hello?
Pardon?
Yeah,
hello?
How do you, from the smooth fibers, how do you get the weight filtration of the singular fibers? I mean, the singular fibers only have a pure Hodge structure. So how do you get a mixed Hodge structure on the?
Yes, so that is the whole thing. Thank you. That is exactly the point. So what I do is that I basically put this limit mixed Hodge structure right on the whole thing. I mean, so what it is really looking at when I see this, right, is that this is on the punctured disk. So this is giving me a way of connecting the whole, so what I'm saying is that for the punctured disk, it doesn't matter which fiber I have, I can put a mixed Hodge structure on the whole thing. Okay, and that, so because as you said that the fibers are smooth. So when the fibers are smooth, their Hodge structure is going to be pure. But I can equip them with a mixed Hodge structure. So if I was to equip them just with the trivial mixed Hodge structure, then things would not work. Okay, so I need to really equip this with the limit mixed Hodge structure, and the limit mixed Hodge structure is kind of I mean, this is the construction that I have to pull back to the universal covering. I have to, so this is, of course, I put a lot of things here under the rug, but this is the work by Deline. So this requires quite a bit of things, but yes, it's exactly this. Thank you. So the idea is this. So if you were to just do the most naive thing that you can think of, that okay, I have the singular fiber has the mixed Hodge structure. I have the smooth fiber which has a pure Hodge structure. I just put the trivial mixed Hodge structure on the smooth fiber, and I get a morphism. No, you can get a morphism, but it is not going to be a morphism of mixed Hodge structures. So the only way I can actually really get a morphism is that I equip the smooth fiber, not with the trivial mixed Hodge structure, but the mixed Hodge structure coming from the limit. Good. Okay. And if I do that, then I really have the specialization map is really it's not just a morphism, it is a morphism of mixed Hodge structures. So I'm really not just connecting the two cohomology groups, I'm also connecting the mixed Hodge structures on them. Okay, but in general, this is neither surjective nor injective, and we don't just want a connection between the two things, right? We really want to study the Hodge classes. So the question now is not just about how to connect the two things, but also how can you intercept all the Hodge classes of the singular fiber from those of the smooth fiber. Okay, so this is the really subtle, difficult technical part of our proof, that, as you will see, that this requires us to basically impose conditions or to try to understand that the Hodge lattice should keep the same rank, basically. Okay, so in very layman's terms, what we need is that the rank of the Hodge lattice needs to remain the same. This is in layman's terms. In a little while, I will actually give more precise definition so that so as I said, all this time I have been using lots of words, using lots of just ideas, and hopefully this motivates a little bit. But in a little while now, I will try to be a bit more precise so that the experts in the audience can see that, okay, I'm not just hand waving. So I need the rank of the Hodge lattice to be equal to the Hodge lattice of the general fiber. And this property I will call, if my family satisfies this property, I will call this a Mumford-Tate family. Okay. Okay, so yeah, so maybe this from here on I start getting really technical. So if there are questions, this is a good point. And also, if people are, I mean, I asked this a little bit earlier, but I don't know if people were listening. So do I know how long I have?
Another 15 minutes.
Huh?
15 minutes.
15 minutes. Okay. So yeah, because I thought maybe I started like 5 minutes later, but okay. So 15 minutes. Okay, that's good. Okay, so now I am going to give a more technical definition of what I mean by this Mumford-Tate family, where the lattice doesn't jump, etc. The rank of the lattice doesn't jump. So for that, I need to give another definition of a Hodge structure. And so I denote by this fat S the Weyl restriction of scalars for the field extension C over R. Okay, what does this mean? It means that for a commutative R algebra A, when I take this fat S of A, I get A tensored C over R, and I just look at the units. Okay, now S is an R algebraic group. Okay. And I gave you this definition of a Hodge structure, this lattice, this complexification and this decomposition and whatnot. There is another definition of a Hodge structure, and that is that a Hodge structure of weight R is given by a non-constant homomorphism of R algebraic groups. Okay, so I have that this Weyl restriction of scalars. This is an algebraic group, and I have having a non-constant homomorphism from this to basically. So V here is my lattice. Okay, so I have a lattice, and now I look at its tensor with R, and I look at that vector space, the general linear transformations for that vector space, and if I have a non-constant homomorphism of R algebraic groups, such as phi, such that over C, the eigenspace decomposition of this morphism phi is basically going to give me the decomposition for the complexification of the lattice, and also this property that phi zv is equal to z to the p z bar to the qv. Okay, so if you're wondering what is going on here, then it's a very, very good exercise to check that this definition of a Hodge structure of weight R is going to imply, and it's going to be equivalent if and only if the Hodge structure, the definition of a Hodge structure of weight R that I gave you earlier. Okay, so you can have a do this exercise if you're bored for the rest of the talk. Okay, so why am I giving this definition? Well, the Mumford-Tate group. So this is a new definition. The Mumford-Tate group associated to a Hodge structure, V phi, so V the lattice and phi this non-constant homomorphism, is the smallest Q algebraic subgroup of GLV, which contains the image phi s. Okay, so I look at the smallest Q algebraic subgroup in there, which contains the image. Okay, this group is called the Mumford-Tate group. So there are, again, quite a few different definitions of this, depending on your viewpoint or what you're really interested in. But this is, I think, the viewpoint that I am most interested in. So I just give it. And also, I think that this is actually one of the easiest ways of understanding it. Okay. But then there is the other one, which is that I can denote by TMNV, V to the M tensors, power tensored with the, I think there's a bracket missing here. Okay, with the dual homomorphism from V to Z, tensor to the N, tensor Q. Okay, so I have this. I define TMNV in this way, and the elements of F0 of this intersect with the TMNVQ of weight 0 are called Hodge tensors. Okay, so obviously, if you've not seen these things before, it's fairly technical. But in this part of the talk, I'm really talking to the experts. I think they already know this very well. So the elements of weight 0 are called Hodge tensors, and they inherit a natural Hodge structure from V. And when V is equipped with a mixed Hodge structure, so V was the lattice, right? So we could have a pure Hodge structure, but also a mixed one in the case when the variety is singular. Then these are weight 0 elements of F0 to this intersect with the for the weight filtration, the weight 0 part of TMN of VQ. Okay, so these elements of weight 0 are called Hodge tensors. Okay, so if you did not like my simple, easy definition of a Mumford-Tate group, the other one, which also most people give in talks, is that the Mumford-Tate group is the biggest subgroup of GLVQ, which fixes the Hodge tensors. Okay, so you have a group acting on these Hodge tensors, and they are invariant under action. So this is another definition of Mumford-Tate group. Okay, and the question is, what is a Mumford-Tate family? Now, if I let pi to be a smooth family over, chi to the unit disk, be a smooth family over the punctured disk, and I fix p greater than 0. Now, for t in the punctured disk, I denote by MT the Mumford-Tate group associated to the pure Hodge structure on H to P chi TQ. Okay, so here, let me explain. So I have been taking all this time, this flat projective family and whatnot, and I say that the only singular fiber is the 1 over 0. And here I'm taking the punctured disk. So all these fibers are going to be smooth. And now for the smooth fibers, I'm saying that the Mumford-Tate group, obviously the Hodge structure is going to be pure, and I denote by MT the Mumford-Tate group associated to this pure Hodge structure. Okay, now I can also equip this general thing, just as one of the audience was pointing out, that of course I can just look at the pure Hodge structure of these general fibers. I can also look at equip this with the whole thing, the punctured disk, with the limit mixed Hodge structure. And so I do that. Okay, and then what? And then I can also look at the Mumford-Tate group associated to a fiber when I'm equipping it with the limit mixed Hodge structure. Okay. And I say that pi a Mumford-Tate family pi is a Mumford-Tate family if the two Mumford-Tate groups are isomorphic. Okay, so they should be isomorphic as algebraic subgroups of the group of automorphisms of the cohomology of the fiber. And this is basically what I'm saying is that, okay, I'm going to say this in words, and I don't know how much sense it's going to make, but basically what I'm trying to say is that I want the limit of the Mumford-Tate groups to be the kind of the Mumford-Tate group of the limits. Okay, so roughly speaking, I want something like that. So on one hand, I have the general fiber when I am not looking at it as a limit mixed Hodge structure. And on the other hand, when I have it as a limit mixed Hodge structure, I want to see that the Mumford-Tate group is the same. So essentially what I will need later on is that I really want to see that somehow taking the limit mixed Hodge structure and then not taking the limit mixed Hodge structure, but just taking the limit of the things gives me the same thing.
There seemed to be a different definition in a previous page for a Mumford-Tate family.
No, I did not define what is a Mumford-Tate family.
There was a definition of a Mumford-Tate family in the previous page.
Oh.
One more page, please.
Okay.
Yeah.
Right. Yes, exactly. Okay. Okay, sorry. Yes, you're right. So here I was being very heuristic. So here I was really I did not define really what was a Mumford-Tate group, right? So I just told you very heuristically, what do I mean by a Mumford-Tate family? So thank you. I did not see who this was, but okay. So the point is this, exactly. So I have the Hodge lattice, right? So I have the Hodge lattice for the fiber, general fiber as it is, and I have the Hodge lattice for it when I look at it as a limit mixed Hodge structure. And I want that the rank of the two lattices is the same. So saying that the rank of the two lattices is the same is roughly coinciding with me saying also that, I mean, I can look at the action. So here, yeah, maybe I could explain more, but I tried to put it under the carpet. So if you do not like this definition of the tensors, then you can think of just what I said before, that you just want the rank of the Hodge lattice to remain the same. But if you're an expert, then you know that what I'm really saying is that the things which are invariant under the action. So I have the action of the Mumford-Tate group on the lattice, actually on the VC and on the VQ. So the complexification and the tensoring with the rationals, and I want those elements to remain the same. Okay. So the Mumford-Tate group is the biggest subgroup which fixes the Hodge tensors. So this is in some sense the actual precise definition. So what I said earlier is that if you freak out at these tensors business and you do not know these things, and it's a little bit scary, then you can just think of very, very layman terms. I'm just saying that the rank of the lattice doesn't change. So I can think of, so what happens is normally that the rank of the lattice jumps, it goes up, the dimension of the vector space goes up, and in general the rank of the group actually falls. So the things fixing it goes down. But yeah, I mean, this is I would need a lot more time to really go through this. So but yeah, so it depends on how you want to see it. So you can just think of this a Mumford-Tate family as something where the rank of the lattice remains the same, or better, more technical and more precise way of thinking about is to think of when you take the complexification and you look at the Hodge tensors, what are the group of Hodge tensors should remain the same. So the things that are invariant should remain the same. Okay, so okay, so this is thank you for pointing that out. So basically what I'm I'm saying is, yeah, it depends on how advanced you are with this, but then you can see it. Okay, so what I want is that the Mumford-Tate group that I think of, I have when I am looking at it as a limit mixed Hodge structure should be isomorphic to the Mumford-Tate group that I have when I just look at it as a pure Hodge structure, okay, for a general fiber. So if this happens, then I say that the family is Mumford-Tate. So obviously all definitions are good, all conjectures are good, but the question always remains, are there any examples? I mean, if there are no real examples for these things, then it just seems very sort of empty. But here, maybe I don't know how much time I will have. So I will just say this. So what happened in, yeah, so I don't know how much time I'm gonna have, but okay. Let me say the story here. So I was invited around 2.5 years ago by Pranav and Rukmini ma'am to give a talk in ICTS on the Hodge conjecture for the moduli space of stable sheaves with the fixed determinant on a nodal curve. And that it was an example of something which was singular, and we showed that actually, me and Ananyo, we showed that it actually does, if you look at the desingularization, it satisfies the Hodge conjecture. Okay, and we really thought that we'd kind of gotten a bit lucky with the example. I mean, we did not know what was really going on. We did some computations and things worked, and we thought, oh wow, this is great. But then after the talk, Professor Simpson actually asked me some questions, and yeah, and then we had some discussions, and then I realized that actually maybe the phenomena that we were looking at was more general. I mean, it was not just that we worked with this moduli space and things worked out. So basically in the last 2 years, I mean, since that talk, me and Ananyo tried to work out what was really happening. I mean, when you forgot about the moduli space and you forgot about the semi-stable sheaves and whatnot, what were the only things you needed, the essence that you needed in order to get a similar result. So basically, if you're wondering, is there really something called a Mumford-Tate family? Then yes, a good example of a Mumford-Tate family is that if I look at smooth curves degenerating to a nodal curve, I know that there's a relative Giesiger moduli space of stable sheaves, which also has this nice specialization property. And actually, in these cases, you can really work out, because you have a smooth family over the punctured disk and whatnot, you can actually see that this really is going to be a Mumford-Tate family. So examples of Mumford-Tate families, things where the rank of the Hodge lattice doesn't jump, or I mean, in more complicated terms, you can see that these algebraic subgroups are going to be the same. These things do exist. And so the result that I'm going to say now actually does have examples. In fact, this result came about as trying to generalize that example. So, and I owe it big time to Pranav and Rukmini ma'am for giving me that opportunity, because yeah, then we wouldn't have guessed it really that, okay, this would just work, or there was anything here. So it's also big thanks to Professor Simpson. So if we have X a projective variety, possibly singular, of dimension n, and we fix integer p such that the dimension of the singular locus of X is strictly less than p, then what we show is that if you have a flat projective Mumford-Tate family with your singular variety, right, being the fiber over 0, and you have that the general fiber satisfies the Hodge conjecture in weight p, then X satisfies the singular Hodge conjecture in weight p. If the Hodge conjecture in weight p minus 1 holds for varieties of dimension n minus 1. So this seems quite, again, technical, but as I said, yes, the examples of such varieties exist. Okay, so, and I don't know how much, I think I probably have to back up soon. So, okay, so I'll just take 5 minutes. So by semi-stable reduction, I know that there exists a flat projective family which has the same fiber as pi 0, and it is going to be regular, and that the central fiber is going to be reduced simple normal crossings. So here I did not have any conditions on how bad the singularities were going to be. All I said is that the dimension of the singular locus needs to be strictly less than p. Okay, so the first thing I do is that I actually put this, I don't consider any fiber. I actually try to reduce it to the case of semi-stable. I use semi-stable reduction to reduce it to the case of simple normal crossings. And I say that with one of the irreducible components being birational to x. Okay. Now, so x was my starting singular variety. Now I denote by y0 the central fiber and E the union of components of y0 except for y tilde. Okay. I.e., so y0 can be written as y tilde union E. Okay. Now, since the singular locus of the central fiber is of dimension at most p minus 1, the hi is going to be of this y thing is going to be 0 for I greater than or equal to 2p minus 1. And if I let u to be the regular locus of x, I can see that actually the graded 2p piece for u is the same, is isomorphic to the graded 2p piece for of x. So furthermore,
can I interrupt you? Sorry, can I interrupt you for a moment if you don't mind? Can you just go back to the statement of the theorem?
Yes. Yes, sorry, maybe I can stop here. It's I mean, the proof is technical. I wasn't sure how long I would have, but I think I'm already running out of time. So I can stop here, but yes. So so I think Balaji was there during the talk I gave in ICTS. So yes, essentially the proof is somewhat generalizing that strategy. So you know that you have your, so as long as you have your Mumford-Tate family, then you can actually tell that the Hodge classes on the singular fiber are going to come from Hodge classes on the whole thing. You can show this as long as you have a Mumford-Tate family. And then you are really trying to use the specialization morphism to...
Can I sorry, interrupt you a little bit, if you don't mind? Suppose there's just a smooth family itself. Suppose everything is smooth here.
Yes.
I suppose it's a smooth morphism. Okay, I mean, there is no singular fiber at all. Then are we trying to say that if you mark a point in the base, say, for example, your delta is a disk, and if you want to prove you want to make a statement about the Hodge conjecture for the central fiber, then what is the correct statement here? I mean, what's the statement here in that case? I mean, you just take a flat, proper, projective, smooth family. Everything will be all right. It'll be Mumford-Tate and whatnot.
No, actually not. That is also a subtlety. Even if I just take a nice smooth family, it need not always be Mumford-Tate, because this is thank you. So this is the issue, that there are I mean, that's why, I mean, there's a lot of technical stuff here, but basically even for this comes down to the Noether-Lefschetz locus. So you have things which even for smooth points there can be jumps in the rank. So there can be jumps in the Noether-Lefschetz locus. So it's not always guaranteed. No. You really need things to have a Mumford-Tate family. If you have a Mumford-Tate family and that this smooth fiber satisfies, a general fiber satisfies the Hodge conjecture, then you can say, given these conditions, that yes, this can hold. If the Hodge conjecture holds for varieties of dimension n-1, then it can hold. But it is not a priori that, okay, you finding a Mumford-Tate family is not as hard as, I mean, it's not a mythical creature. They exist, as I just gave the example, but it is not trivial. So it's not that anytime I take something smooth, I will have a Mumford-Tate family if I just take a smooth family. No, this is unfortunately what made, I mean, we were really struggling with this the last couple of months. We were really trying to see what all other things we can get, but it is more complicated than that. So if I had time, I would have added more slides about these things, but I didn't. And so so it's not God-given Mumford-Tate families.
Okay.
Sorry. So but thanks a lot for bringing that issue, because this is exactly what you would think, that okay, if you have a nice smooth family where this is, then But no, it doesn't work like that. So, and you really have to go through the calculations, and you need to know these subtle things about the Noether-Lefschetz locus. So, but yeah, that's an excellent question. Thank you. Okay, so I think I will just skip the proof because I don't know if my audience is still awake. But yeah, I mean, I will give the slides maybe to Suratna, and you can go through it. And of course, we are hoping to, again, coming back to Balaji's point, we are hoping to basically give as big a list of Mumford-Tate families as we can. So we are still working a little bit more on that. So we know that Mumford-Tate families exist, such as in the case of the moduli space of sheaves, when you're looking at a family of smooth curves degenerating to a nodal curve. And there are also examples, again, moduli space type examples from Hilbert schemes, etc. So there are quite a few examples, but yeah, we want to give many more examples, and we are working a little bit more on that. But hopefully by August we will put this online. So once it's online, then anyway you can see the proof more carefully. So here I had given all the the strategy of the proof and whatnot. But yeah, I don't have too much time to go through this. So I'll stop here. Thank you. Hello.
Yeah. Can you hear me?
Hang on. Yeah, I can hear you.
Could you say something about the theoretic version of this result? Or is there any work theoretic section?
Sorry, I
Can you hear me now?
but then
Are there any p-adic versions for this?
are there any p-adic versions? Oh no, I have no idea. I don't know any kind of how Hodge conjectures work for the p-adic version. I have no idea about that. I don't totally think so, but there's been so much work done recently on p-adic stuff, especially with the Hodge theory. I think there might be things, yes, but I don't know. I'm sorry.
So I have a question. So actually, this example you have given, one example is the moduli of bundles. So
Hang on. Maybe,
just one couple of examples for this Mumford-Tate family. How do they look like?
still can't hear you very well.
Yeah.
Go on.
Which is the example you have provided for a Mumford-Tate family?
Yes.
Which is the example actually? Take a moduli space of rank 2 bundles, is it, on a curve?
Yes.
Rank 2 and in co-prime.
Yes. Rank 2 co-prime. So we worked it out in the rank 2 case. Actually, I think you could do it for any rank. Yeah, so we had it. So yeah, maybe I could speak a little bit more about that. But basically, the thing was that we already knew, thanks to the work of Balaji King Newstead, we knew that for rank 2 fixed determinant, the moduli space of sheaves over the smooth fiber, the general fiber, satisfies satisfies the Hodge conjecture. And the thing was that the big thing was to see, which we didn't figure out then, was that this really also worked because this was a Mumford-Tate family. So that we kind of actually figured out later on when we were going, we were submitting the article to the journal, and there were also some questions by the referee. So that actually helped us clarify this more. But yes, that forms a Mumford-Tate family. So that was an example. You do not need the rank to be 2, because the result of Balaji King Newstead has been generalized for any rank by Biswas Narasimhan. So I think that is fine. Yeah.
So basically, is this the second example? So you have a family of curves, and then so that one fiber is a singular fiber, I guess.
Yes.
Then you associated moduli space with rank 2 and degree 1, for example, and then you are looking at the limit of that function. That is the example you are quoting.
Yes.
So okay, so instead of this rank 2 case, how about rank 1? You just start with the family of curves, especially nodal fiber, and then you take the family of associated Jacobians, because
Right.
Jacobians suppose it's a general family, you know, the Hodge conjecture is true for the generic member. So what do you know about the special fiber? I mean, does it form a Mumford-Tate family as well?
Yes, yes, that's an excellent question. Yes, it does. It does form a
Can
Mumford-Tate.
can I interject a little bit if you don't mind?
Yes, please go ahead.
Yeah. I just sorry to interject. I think you have to fix the determinant to ask these questions. So I do
Yes.
not know that the Jacobian question is relevant here, and therefore in the higher rank case, I don't see why you should have a good Giesecker degeneration in the fixed determinant case. That's a non-trivial.
Yeah,
So I don't think you
that's-
can directly do anything for the higher rank from this. In the rank 2 case, it's a very special situation, especially when you degenerate to a reducible curve. This is there in Surutno's thesis, that you do have a good situation there, but higher rank, I don't think it's a straightforward generalization.
Okay, so it's okay. So whenever I ask people that can you do these things for higher rank, they said yes, but I actually only worked in rank 2. So thank you, Balaji. That is correct. I do not totally know for higher rank whether it works. I believed that it works. So thank you for the correction. That is I do not know for sure. We only worked in rank 2. That is
I'm just trying to say that the degeneration theory, Giesecker degeneration, is highly non-trivial for fixed determinants, except in rank 2 and reducible curve.
right.
So that's a very special situation. And Hodge conjecture, otherwise you have the determinant map and you get connected to the Jacobian problem. And the question from audience, I guess it was Jaya who was asking the question. So I do not know whether the Jacobian case fits into this kind of picture, the moduli picture. Moduli, the fixed determinant case is what fits. That's what I understand.
Yes. No, I think that actually the Jacobian case also fits into the picture. So I would think so, because we were, so the thing is, we worked everything out kind of backwards. So we did our computation, we worked things out, we wrote the article, and then later on, as I said, Professor Simpson's question made us think that maybe this was a more general phenomena. And then when we were writing when we had comments from the referee for the article, we tried to clarify some things. So we actually did show this thing of the Hodge classes of the limit being the Hodge, the limit of the Hodge classes. So these kind of things we had to both show for the Jacobian as well as for the moduli space. So I would.
Sorry, are you saying that? Sorry to interrupt. Are you saying that if you take a smooth curve degenerating to a nodal curve, okay, and you take the Jacobian and look at the degeneration, this is something like the compactified generalized Jacobian in the nodal curve, then this is a Mumford-Tate family?
Yes, that at least in the case that we were looking at for the irreducible nodal curve, yes, I would say so. This was we did not really work exactly on this question. We worked it for the moduli space of higher rank, but yes, I would think so, that yes, this is one of the cases where things again could be good. I do not know if it would be the case if you make the singularities very bad or whatnot, but for the irreducible nodal curve case, yes, I think we had this. So yeah, that would be my answer. So but this is an excellent, these are excellent questions. So I'm really missing not being there in person, because yeah, we could discuss more such examples. In fact, so what happens is that I think that this Mumford-Tate families thing would also be there for things that, so as you pointed out, that is it going to be for smooth families? No, it's not going to be there for smooth families. But in the reason why these were Mumford-Tate families to begin with was that actually the cohomology was quite simple in a sense. So the reason why I would say that for the Jacobian things worked is that, the reason why this moduli space of rank 2 bundles, the one that we were considering, turned out to really be to work for this Mumford-Tate family thing, is that we were really using a result of Mumford and Newstead, which said that the cohomology of the moduli space is actually governed by this. You have the H1 of the curve, and you have this isomorphism to the H3 of the moduli space. Yeah, so we have a Mumford-Tate type result, which said that basically you can boil down understanding the cohomology of the moduli space to that of understanding the cohomology of the curve. So we were, so this made, this was one of the reasons why the moduli space thing was actually a Mumford-Tate family. The cohomology was not so complicated because the cohomology was coming from the cohomology of the curve. And so in most of the cases, when you are trying to understand the Mumford-Tate family, it's not just that you want things to be smooth, it's that you really want to be able to understand if the cohomology is simple enough. And so, yeah. So, because it's not easy to check whether something is a Mumford-Tate family or not. So you really have to do a lot of computation. So if the cohomology is very complicated, then this is not easy to check. I don't know if it's much help.
Thanks a lot for the nice talk. Let's happy.
Thank you. Thanks a lot.
I have one question. So just like example presented, so the special curve is a reducible curve. That's what I understood from Balaji's remarks. So actually Suratma also said that okay, in that case the moduli space so it becomes a reducible variety. Is that right? So whatever statement you're saying. But Balaji's remark is reducible curve. So reducible variety.
Yeah, yeah.
when I'm free. Yeah, just couple of minutes. So I think
Yeah, sure, no problem, no problem.
everyone is coming back.
Yeah.
Very nice. Very happy.
Okay, so the last speaker for today is Anand. So he's going to talk on topological and geometric obstructions through deformation of device. So Ananya, please, you can start.
Thank you. Can you hear?
Yeah.
Everything is okay. Thanks. Thanks for the invitation. I would have liked to be in person, but I kind of did not plan it well enough. So maybe next time. I imagine this is a periodic event, so maybe next time I'll be in person. So, okay, so I will try to talk on some topological and geometric abstractions to deformation of devices. Um, so the starting point is always I'm going to work with a smooth projective variety over the complex numbers, and I look at the local complete intersection subvariety in here. And we can look at an infinitesimal deformation of the smooth projective variety. And we want to ask, when does Z lift to a local complete intersection subvariety in this infinitesimal deformation? So typically this is what sometimes is known as the geometric obstruction, because we are trying to deform a geometric object. And now the goal, what would be, is to relate this to somewhat of a topological obstruction. And some of it is already exists. So we are trying to understand the existing theory and trying to refine it a little bit. So what we should first observe is that the answer to this question, whether given any uh, subvariety Z, was there a question? So we want to ask, if there is given a projective sub variety is Z, um, can we lift it to a infinitesimal deformation? And for example, one can easily take, if you take a family of, say, smooth projective surfaces with just one fiber containing is a surface containing a line, and the nearby fibers not containing a line, then you will never be able to infinitesimally deform this line to the nearby fibers. So you definitely need some more conditions to answer this question reasonably. So the new assumptions comes a little bit from Hodge theory, and this is what will be I will call the topological obstruction theory. So what I am going to try to do is that I'm going to relate this question to the classical question of deformation of the cohomology class of Z and of this subvariety. So to make this more precise, what we have is in the infinitesimal case, we can look at the Derham cohomology, and this is simply the higher derived image of the Derham complex. And so this is a bit formal. So I will make this a bit more down to earth in a moment. So this is because things are a bit more complicated when you look at over a Artinian ring. So that's why this is a bit formal. So, but I wanted to pose in this language for the experts. So what we know is that the this curly H2P theorem, this is a vector bundle on it's a locally free sheaf on something that is fat point. It is just a speck of an Artinian ring. And what we are interested in is what we call Hodge classes, are the flat global sections of the so if you look at the theorem of Deligne, the theorem of Deligne tells you that this vector bundle H to B dr, this can be decomposed into direct sums of other vector bundles which are of the form R 2p minus q, if a lower star of omega q. So now, to make sense of Hodge classes, we want to restrict to the case when q equals p. But you can also ask whether this, you can always have sections that restrict to the cohomology class of this subvariety Z. But what is important is that this section is in some sense flat. So again, this is a bit complicated over an Artinian ring. So I will very soon change to the more understandable setup. So what I want to say is that what I want to ask is that if you add this assumption that this cohomology class of Z lifts as a Hodge class, okay, so the cohomology class of Z, so for people who know, is we know that this is already a Hodge class in X, and we're asking if this lifts as a Hodge class in the neighboring fibers. In this setup, it's a really infinitesimal neighborhood. Then can we give a positive answer to this question? Okay. So to make this thing a bit more simpler, let me talk a bit on the Hodge theory. So here I am only going to look at smooth projective varieties. So we only have the pure Hodge structures. So we have the Hodge decomposition of the kth cohomology group of X in this form, which we saw in the previous talk. And it satisfies the condition of conjugation where p k minus pth part of the cohomology is isomorphic to the conjugate of the k minus p pth part, and there is a canonical isomorphism of the p k minus p with the cohomology of p differentials. And what are the Hodge classes in here? These are normally we always look at the even cohomology groups, and we want to look at the PP classes in the complex in the Hodge decomposition, and we want to look at the rational points in this vector space. And this is a very subtle point, and it's very important. Normally in the dimension of HPP, it is normally much higher than the rank of this intersection. So there are much more basis elements which are not rational. So this is a key object of study in Hodge theory and variations of Hodge structures. And what you immediately want to associate is the cycle class. When you are given a closed subvariety, you can already associate a cycle class. And how do you do that? Is that you start with the subvariety of codimension P, you take a resolution, and once you have a resolution, you will have a JSON map. So yeah, see, Z tilde and X are smooth. So you will have, there are too many P's. But don't worry about the morphism. So you will have a JSON map going from the 0th cohomology of Z tilde to the H2pth cohomology of X. And the image of 1 in under this JSON map is what is the cohomology class of Z. Now, it's a little bit more tricky to show that this cohomology class is indeed a Hodge class. We will go through this proof a little bit later on, which will tell you why this is really a Hodge class, but that is comes a bit later. So I want to get to the question that we want to answer. So for this, now we look at the smooth projective family. So here, all the fibers are smooth, and I fix one fiber on in this family, let's say over the point, say O. In I fix a base point and I look at the special fiber over this. And here we will assume that B is an irreducible complex manifold, and I also choose a Hodge class. So you can choose an element in the PP class, which is also rational. Now, here this is the part where you need to use that this is really an irreducible, B is an irreducible complex manifold, because now if you using Ersman's theorem, you can show that all the fibers, or all the cohomology H2P of all the fibers are isomorphic. In fact, they will form a local system. And this is the local system that we take. It's the 2p R2p of pi lower star of Q. And in this, we know that local systems behave in the sections of the local system are quite well behaved. So gamma will give rise to an unique section in this local system. And then we can talk about Hodge locus. The Hodge locus is the all the points in this complex manifold such that when you evaluate at any point on the base, you get back a Hodge class. So when this is just a Hodge, gamma bar is a section in this local system. So at every point, it takes value at every point over small b, it takes value in H2P of xb, and then you have the Hodge decompositions on xb. So you can ask whether this value really is a Hodge class. And if it is, that point belongs to the Hodge locus. And if you look at it slightly in a more analytic sense, you can prove that this is a analytic variety, and it is given by HP plus 1 p minus 1 x number of equations. This follows somewhat from the Griffith's transversality. So what one can check is that the Hodge class deforms in a infinitesimal neighborhood. It will deform only to the HP plus 1 p minus 1 part. So to ensure that this remains a Hodge class, you just need to look at the locus where this does not happen. In particular, that this equation vanishes, the p plus 1 p minus 1 part. So now we want to, the question that I've asked in the beginning was that when does the projective variety Z lift to a local complete intersection? And then I reformulated it in the terms of, if we assume that the cohomology class of Z lifts as a Hodge class, then can we say that Z deforms as a local complete intersection? Now, this can be understood in this statement that the cohomology class of Z deforms as a Hodge class. This can be made more explicit in terms of the tangent space of the Hodge locus. So that's why we look at the Hodge locus, because now we have the cup product map. And the cup product map is induced by the inner multiplication of omega xp with the tangent sheaf. And this maps to omega xp minus 1. And then you have to take the cohomology in the correct way to get this cup product map. And now we combine it with the classical Kodaira-Spencer map. The H1 of the tangent sheaf contains all the space of all infinitesimal deformations of X. So, and the tangent space of B is just a subset. So there is a natural map from the tangent space at this point O of this complex manifold B to the, in some sense, the universal family of all infinitesimal deformations of X. So now we are going towards the tangent space to the Hodge locus. And before we get there, we had this cup product map. So if we take the Hodge class is an element of HP omega XP. And now we take an element of the tangent vector on B, then take the image under the Kodaira-Spencer map, then we can apply the two to get apply the cup product map to these two entries to get an element in HP plus 1 omega XP minus 1. Right? So we get a map from the tangent space on B to HP plus 1 omega XP minus 1, sending T to this cup product. And what we can this is the classical result in Hodge theory, is that the tangent space to the Hodge locus is simply the kernel of this map. Okay. So now let's go back to our question. So we start with a local complete intersection subvariety. We take the cohomology class, and now we are asking that if I look at the tangent space where I already know that the cohomology class of Z deforms as a Hodge class. In particular, it belongs to the tangent space of the Hodge to the Hodge locus. Then can I say that this subvariety Z lifts as a local complete intersection in XT? So the answer is not obvious. Now we have to go through quite a few steps. So because in some sense, that's why I think of this as a topological obstruction, the obstruction to the deformation of the cohomology class of Z to a Hodge class. This is in some sense a topological obstruction, which does not necessarily imply the geometric obstruction of lifting it as a local complete intersection. This need not vanish. Even if the topological obstruction vanishes, the geometric obstruction need not vanish. So I will keep repeating this from time to time, so to make this clear. And so what the next step would be to relate these two different obstruction theories. So one is this infinitesimal deformation theory of Z, where I look at when it lifts as a local complete intersection, and the topological one, which is encoded in the tangent space to the Hodge locus. And the main ingredient for this relation is given by the Bloch semi-regularity map. So let's review what is Bloch semi-regularity map. It's not a very difficult construction. So we start with X a smooth projective variety, and then a local complete intersection subvariety in here of codimension P, and we have the differential operator from the, so the dual of the normal sheaf, it is simply the ideal sheaf of Z mod ideal sheaf of Z square going to omega 1x tensor OZ. Note that this is actually OZ linear. If it was just from going from the ideal sheaf, then it will not be OZ linear, but because we are modding out by IZ square, that makes this map into OZ linear map that will play a role in what is coming up. So then we take the wedge product of the P minus 1 times, where P is the codimension of Z, and we get this map between the wedge products. And now we are going to transform this, make some equalities to transform this map into something slightly more computable. that will give us the semi-regularity map. So we are translating the problem slightly now. So the first step would be to identify this homomorphism between the p minus 1th wedge product of the normal sheaf. There should be a dual here. It's a typo. So in the first step, there is a dual nzx dual going to omega xp minus 1 restricted to z. And what you can now do is that the wedge p minus 1, you can write it as wedge pth wedge product tensor with pth wedge product of the dual of the normal sheaf tensored with the normal sheaf. And the advantage of this is that we have the adjunction formula for the pth wedge product of the dual of the normal sheaf. And if we substitute that, that is simply the canonical sheaf of Z dual tensored with kx. Okay, I should say the dualizing sheaf because Z need not be smooth. So this will, I can make this substitution. And what I do next is that I want to exchange. I want to take omega xp minus 1 from the right. I want to take it to the left. And I want to take kz dual tensored with ncx from the left to the right. And this gives me homomorphisms from omega xn minus p plus 1 to kz tensor ncx dual. So this means, so I started with an element in here in the first, the p minus 1th wedge product of D was an element in the first hom. And now I am ended up in the totally different element. And I go one step further. What I want to do is that I want to take the cohomology. In particular, if I look at this n minus p minus 1th cohomology, I get this map. If you see, this is omega xn minus p plus 1 to kc tensor ncx dual. Okay. And then I can apply Grothendieck duality to, and we'll get the semi-regularity map. So Z was of codimension P, so that's why Hn minus P minus 1 becomes H1 NZX. The dual of it becomes NCX. And X is of dimension N, so the dual of Hn minus P minus 1 omega X becomes HP plus 1 omega XP minus 1. So now we have the semi-regularity map. It's quite straightforward. It looks a bit strange and with some ad hoc computations, but it has very nice geometric properties, which we will see. And if this semi-regularity map is injective, then we call the corresponding subvariety is called semi-regular. And now there are, so let's, this construction was quite complicated in some ways. There is a more direct computation in the case when p equals 1. And this is more classical. This goes before Bloch. And this is by Kodaira-Spencer. And this gives you, this says that the Bloch semi-regularity map coincides with the co-boundary map. So if you just look at the semi-regularity map, it goes from the first cohomology of NZX. So now if p equals 1, then the target is going to be H2 of OX. So you see, we are already in the setup of a co-boundary map of the short exact sequence. So, and indeed, this is the case that the Bloch semi-regularity map is the co-boundary map coming from the short exact sequence. Okay. So now, are we any closer to relating these two obstruction theories, the geometric and the topological one? So we go back at the setup as before, and it was shown by Bloch that the, so first this is where this is the key. you have the cup product map with gamma, which we saw defines the tangent space to the Hodge locus. So what Bloch proved is that the cup product of with this with the cohomology class of Z, this map going from H1Tx to HP plus 1 omega xp minus 1, this map coincides with something a bit more natural, where you go from H1Tx by restriction to H1Tx restricted to Z, and then from H1Tx restricted to Z, you can go to H1NZX. This is simply the dual of the the differential operator that we saw in the previous slide. This is just the dual of that. And then this is the missing ingredient, was the semi-regularity map. So if you take this whole composition, this coincides with the cup product map. So now what we are, so this is topological abstraction. So now there is a topological abstraction. What we will see is that there is a geometric part in here as well. So let us call the map going, so the first, so in this composed morphism that we have, we want to not look at the semi-regularity map. We want to stop at this H1NZX, and we want to also compose this further in the beginning, in the starting, with the Kodaira-Spencer map. So we look at the Kodaira-Spencer, the composition going from the tangent space to the complex variety to H1 of the normal sheaf. So you see the last two arrows are the same as the first two arrows in this composed map in the theorem of Bloch. So you will now see that there is the geometric obstruction is captured by this map alpha. So that's why it is important to see the comparison. So this is a kind of a standard result in deformation theory. I do not know who proved it first. So this alpha that we have, alpha t goes to 0 if and only if, this is even stronger, if and only if Z lifts to a local complete intersection in xt. So now we have a better understanding of the geometric obstruction. So the geometric obstruction lies in the image of alpha. Rather, it lies in H1NCX. So this means that if alpha t equals 0, then t is in T0, the tangent space of the Hodge locus. You see, the tangent space of the Hodge locus is the kernel of this cup product with gamma. And because of this theorem of Bloch, we know that cup product with gamma is the same as this composed map. And alpha t equals 0 means that it is already 0 in H1NZX. And then if you compose with the semi-regularity map, it will of course remain 0. So this gives us the conclusion. So what this had told us is that if Z lifts as a local complete intersection, then the cohomology class of Z also lifts as a Hodge class. But our original question was the converse. So we wanted to go the other direction. So before we proceed, so let's do a bit more exercises about what does semi-regular varieties look like. So let's look at an easy example. Is when we look at the space of all smooth degree D surfaces in P3. Okay, then we take a point in this space and look at a non-singular divisor contained in this in the corresponding smooth degree D surface. The good thing about in this case is that the canonical sheaf has a very nice description, and a lot of the computations are much simpler in this case. So what we can see is this main object of our interest, H1 of NZX. The dual of this coincides with the global sections of the dual of NZX tensor with KZ. This is just simply the set duality. And then if you use the adjunction formula and then you substitute for the value of Kx, you will get that this is just the global sections of OXD minus 4 restricted to Z. Okay, so what this tells you is that if D is less than 4, so there are no global sections. then there is H1 of there is no geometric abstraction. So of course there is no topological one as well. So this means that the tangent space to the Hodge locus coincides with the tangent space of the whole space of B. And every Z deforms as a local complete intersection. Now D equals 4 is what is known as a K3 surface case. It is a bit more interesting. And in this case, the H1 NZX, which will be the global sections of OXD minus 4 restricted to Z. This is going to be just one dimensional. And this means that either we can have the tangent space of the Hodge locus is the entire tangent space, which happens if and only if the Z is actually defined by one equation globally. It's given globally by one equation, or if that is not the case, then the tangent space is definitely one dimension lower. So this one was D equals 4, D equals D less than 4, D equals 4. This one we understand very well. So what about higher degrees? What are the semi-regular divisors in this setup? So because this is a complete intersection, this is a hypersurface in P3, we know that the H1OX is 0. So then if you look at the same short exact sequence, which we were seeing from the result of Kodaira-Spencer, which gives the description of the semi-regularity map, we see that Z, any of the divisor in X is in this setup, in the setup of hypersurfaces in P3. Divisor in a hypersurface is going to be semi-regular if and only if the line bundle OXZ, the H1 cohomology of this vanishes. So this is a very explicit description. So we can use the Sear's vanishing to produce lots of examples of semi-regular divisors. Now, the one thing I wanted to, maybe I should say after this, is that why are we so interested in semi-regular varieties? Because semi-regular varieties are very closely related to a classical problem known as the variational Hodge conjecture. And the variational Hodge conjecture is simply tells you that if you are given a family of smooth projective varieties, and sorry.
One question. Can you just recall the definition of semi-regular divisor?
It's when the semi-regularity map is injective.
How?
Okay. Any other questions? Okay. So if you going back to the variational Hodge conjecture, we look at a family of smooth projective varieties where we fix a base point. We look at the local. So this I am kind of taking a slightly special case. Normally you can take Z to be any algebraic variety, but for our situations, let's keep it simple. So I take that Z is a local complete intersection subvariety of codimension P. Normally you can take any algebraic subvariety, which need not be local complete intersection. So and then you look at the cohomology class of this local complete intersection subvariety. And then you want to ask that if in some sense, if the cohomology class of this subvariety deforms as a Hodge class, if and only if it deforms as an algebraic cycle, if and only, sorry, let's make this a bit more precise. So the Hodge class, we know the definition of the Hodge locus corresponding to this cohomology class of Z, and the variational Hodge conjecture claims in a slightly weaker form that the value of this the global section of the local system that we constructed in the beginning, that tells you where gamma deforms, what value gamma deforms to in the cohomology class over all the fibers. So gamma, this tells you that the gamma deforms to a Hodge class if and only if the corresponding Hodge class is algebraic. I'll repeat this once more. The Hodge class gamma deforms to a Hodge class in one of the fibers if and only if it deforms as an algebraic class. If it even only if it deforms as an algebraic cycle. Okay, in our setup, it is much more simpler. It is not just going to be an algebraic cycle, it is going to be an algebraic variety. So let's maybe move to that part. So if Z is, if you to start with Z is semi-regular, then you can take that the Hodge locus actually parameterizes all the points where Z deforms as a local complete intersection. In particular, you can, if people familiar with the notion of Hilbert schemes, can see that the Hodge locus corresponds to some kind of image of the flag Hilbert scheme. So, the deformation of Z was geometric, deformation of the Hodge class was topological, and if Z is semi-regular, the both obstruction theories coincide. This is what we know. Now, what is the tricky part here, which motivated our work, is that this notion of semi-regular is very strong. So there is lots of examples, even in the surface case, of divisors, of Cartier divisors in surfaces, which are not semi-regular, but which satisfies the condition of this variational Hodge conjecture. So if our goal is to understand the variational Hodge conjecture a bit better, then we probably need to refine this notion of semi-regularity a bit more. So this was the main motivation. And before I go to that, so some other results on this field of semi-regular varieties is that we can ask in a different way. So the semi-regularity is a notion of the embedding. Something can be semi-regular under some embedding into a projective variety and might not be semi-regular under some other embedding. So that's why semi-regularity is a bit of an ambiguous notion. So what one can check is that if you start with a smooth projective variety, say of dimension m, then you can always find a smooth projective hypersurface in so you always will want to embed it into P2m plus 1. If you can always embed it in a smooth projective hypersurface of this dimension. For lower dimension, it does not guarantee that there is a hypersurface if you go lower than m. You can always embed Z into a hypersurface in P2m plus 1 such that Z is a semi-regular subvariety in this hypersurface. This is always possible. This just involves a little bit of analysis of the definition of the semi-regularity map and playing around with lots of short exact sequences. So it's not hard. So if we want to now, we now try to refine this notion of semi-regularity a little bit more. We are trying to, what we will try is that we will make it a bit more of a local notion in the sense of local cohomology, so that it is a little bit more computable. So we, in the setup, just as before, we have a smooth projective variety and we have a local complete intersection subvariety of codimension P. And we know that we can take an open cover of this X such that on each of these open cover, it really is a complete intersection. It is given exactly by P equations. And so these are just the standard techniques that is known from long time. This is one of the ways of showing that the cohomology class of Z is actually a Hodge class. So now, as I had advertised before, now I am back to that setup where back to this place where I can argue that the cohomology class of Z is in fact a Hodge class. And this is one of the proofs where you look at it in terms of the check cohomology. So going back, we have this covering UI where each of the, where Z is a complete intersection. Then we take another further covering where we are removing the locus where it intersects Z. And the reason will come clear very soon because we are going to look at the local cohomology. An important observation is that this differential form is going to be a cocycle in the p minus 1th. It will be a check cocycle in the p minus 1th check cocycle for this covering of ui. This is a covering of ui removed minus the intersection with z, and in there we have this check cocycle. And now here we are. So this check cocycle will give us, this is a section, as you can see directly, that by construction, this is a section of the R in ui of rp minus 1 of j lower star of omega p x minus z. Okay. And now for the second equality, this is a fact from local cohomology, which is not very enlightening, so I skipped that part. So here now we are looking at a global sections of a local cohomology. We are already in that setup. And now we will see that there is more information to be extracted from this local cohomology. So just a brief revision for people not familiar with local cohomology. It is very similar to normal cohomology with the added condition that you look at the sections which are supported on the subvariety. So, and it can, you do not even need a variety for this. So you can start with a topological space, you look at a closed subspace and a sheaf of abelian groups on this subspace, and we look at gamma z of f are the set of sections which are supported on z. And this is why this is for any topological space. And then we know that the category of sheaf of abelian groups have enough injectives, so we can take the right derived functor on the in this category for any on any sheaf of abelian groups, and this gives you the straight HPZ. This is really a cohomologic group. And now we also like to associate a sheaf. So this is a sheaf which is associated to the pre-sheaf, which takes an open subset in your topological space and maps it and gives you back the local cohomology group with support in the Z intersected U. So these are the main tools that we are going to work with. Okay. So now this was just a sidetrack. Now we go back to our original notations of where I had a smooth projective variety and a local complete intersection subvariety in there. And this is a non-trivial result that these local sections on UI is glue to a global section on this local cohomology sheaf. And indeed, the cohomology, the class that we have, is simply the image of this global section under this natural map that we have. This is standard algebraic geometry. It's even there in the Hodgson's book, this map. Good. Now, to understand, so now if we want to refine the semi-regularity map, we need to understand the semi-regularity map a bit better. So we had some description which was quite algebraic in the sense that it was just looking at slightly of a global picture. We were just looking at the homomorphism of sheaves. Now we want to look at it in a slightly more local setup. In particular, we want to interpret it in terms of the inner multiplication. So we should definitely make sure that our domain and the target are correct. So our domain for the semi-regularity map was H1, for global sections, H1 of NZX, and the target was HP plus 1, omega XP minus 1. So if we can write a inner multiplication in here, then we can take the H1 cohomology of this, and we can almost get there. So I'll come there. So this inner multiplication is a very natural map. It's if you take a section, local section in of this normal sheaf. This takes you an element of this ideal sheaf. In fact, these equations that I mentioned previously, these F1i's on all these FPI's, these are elements in the ideal sheaf. So you simply need to, what you do is that you slightly modify the previous so construction that you had. We had this construction that this was what was giving us z. So now we are going to give the inner multiplication on this. So it is a very obvious thing that you would do, is that we want to keep the I was dividing with, the denominator remains the same. It is just the product of f1i's to fpi's. It's just that the numerator changes because I am applying the inner multiplication there, and the inner multiplication just is the sum over all j's of this local section beta i's applied to fji. Now once you apply beta I to fji, you will end up with an section on oz intersected ui, but you want it to be an element in oxuy. So you need to take a lift. You need to take a lift of this section, which I denote by tilde. And the remaining of the differentials, df1i, they remain the same. I only remove the dfji's. And you can check that this map is well defined and does not depend on the choice of the preimage. So as I promised before, that I take the first cohomology of this map, and it was shown by Bloch that the semi-regularity map is simply the composition. It simply factors through this h1 of this inner multiplication, and the second map is the natural map. So now we want to look at this thing. We do not want to go all the way to hp plus 1 omega xp minus 1. We want to actually just focus on the local cohomology, hp plus 1 z omega xp minus 1. Okay, so suppose I have this, I start with this. So the question was that what are the conditions when z lifts to a local complete intersection? We know that if z lifts to a local complete intersection, it goes to 0 under this psi. Under this map psi, it will go to 0 if z lifts. Now suppose that it does not lift. Suppose it does not lift, means that under psi it is not 0. Then will it be 0? And if you apply again h1 of this inner multiplication. So what I'm asking is that if under this inner multiplication of this 0, if h1 of the inner multiplication with z composed with psi t equals 0, then can z lift to a local complete intersection? And the answer is a little bit surprising, because it is not, does not look, it is an yes or a no totally. What happens is that this means if it vanishes, if for a given t, the h1 of this inner multiplication with z composed with psi t vanishes, if and only if there is a multiple of this Cartier divisor that lifts to a local complete to a Cartier divisor in xt. So it is possible that z does not lift to xt, but a multiple of z lifts to xt. This can happen because we do not only know what are the elements in the linear system. A linear system can have very non-reduced candidates, and we cannot avoid this situation. So immediately, by breaking down the semi-regularity map into this local cohomology, we already see that there is a new obstruction to this geometric deformation of z. So we what we do is that now we introduce a slightly weaker notion. So we have this same notion as before. we know that the abstraction to, because we are now in the divisor case, so the abstraction to deforming the cohomology class of Z as a Hodge class lies in H2 of this OX. And the question is that can we refine this abstraction space? So this is this new map that we want to study instead of the classical semi-regularity map, is that instead of we introduce some new proper closed subvariety, and you can take T to be some points. So T can be really anything. This is the yeah. So for T as a closed subvariety in Z, you have a natural map going from natural restriction map going from OX after removing T to the one of OX removing Z. So this is the natural restriction map. And then the next map is a natural co-boundary map coming from the local cohomology of OX with support in Z. And now, if we consider the same smooth family as before, what we can see is that there always exists. So this is in the semi-regular variety case, we know that if a variety is semi-regular, then the topological abstraction vanishes. But here we see that there always exists a subvariety in Z such that the obstruction space, the topological obstruction space, no longer lies in H2OX, it lies in a slightly smaller space in some sense. So what we prove is that there always exists a subvariety T in Z such that for any element in the tangent vector, the cohomology class of this divisor deforms to a Hodge class if and only if the image of this tangent vector under this composed map goes to 0. And this motivates this slightly weaker definition of T semi-regularity, which depends on the subvariety T, is that if T satisfies this notion, then we call that Z is T semi-regular. And in the beginning, the previous theorem, we saw that it is possible that if H1 of this inner product composed with psi is 0, then a multiple of Z deforms. So suppose that Z deforms if and only if the multiple deforms. Suppose we are in this situation, which we call is saturated. So the more technical condition will be that the restriction of H1 of this inner product map restricted to the image of psi is injective. So if this is saturated, then we can show that the previous notion of the semi-regularity is very strong in the sense that Z is semi-regular if and only if Z is T semi-regular for all proper subvarieties T in Z. Okay, so I stop here. Thank you.
Are there any questions, comments? Okay, there are no questions. So let's continue again.
Thank you.
Continue. So then we will listen tomorrow morning.
Kind of. So, yeah, tomorrow we'll do kind of zero mind. Yeah, one more announcement is that for the investment form, so those will not yet collected from this collected from our Algebra and submit to her as well. Thank you, Anna, for your time.
Thank you.
Great. So it looks like you all are here. Just a second is for us. I don't know. I'll be okay. Tell me the what time you want, but